have done Ohm's law before, and Ohm's law is useful in dealing with simple electrical circuits only. Now, the study of circuits containing more than one source of EMF becomes difficult just by using Ohm's law. Hence, in the 1842, Kishkov put forward the following two laws, which are known as Kishkov's voltage law and Kishkov's current law. Okay, the first law is known as Kishkov's current law, and the second law is known as Kishkov's voltage law. Now, these laws, they are used to study complicated circuits. So we'll come to the first law, which is Kishkov's current law, or KCL. Now, this law states that at any junction, the algebraic sum of the current entering the junction in an electrical circuit is equal to the current leaving the junction. For example, we have in the diagram a junction to point O, and here the current I1, I4, they are entering this junction, and the current I2, I3, and I5, they are leaving the junction. So according to Kishkov's current law, the sum of the current entering, which is I1 plus I4, will be equal to the sum of the current leaving the junction, which is I2 plus I3 plus I5. Now this is Kishkov's current law. Now we have, remember, we have used this law while studying a combination of resistors in parallel. Okay, there the current entering is I and the current leaving the junction is I1, I2, and I3. So if we can recall that, we have used this law in obtaining the expression of the equivalent resistance in the parallel combination. So this is Kishkov's current law, and this law is based on the principle of conservation of charge, which means that in an electrical circuit, a point can neither act as a source of charge, nor the charge can accumulate at that point. Hence, there is no charge at point O. So the net charge usually at this point at the junction will be 0, because the charge entering will be equal to the charge leaving. So this is the law of conservation of charge, and that is what it is based, this Kishkov's current law is based upon. Then the second law, which is known as Kishkov's voltage law. Now this law we have applied while obtaining the expression for the internal resistance of a cell. And according to this law, it states that in any closed circuit, the algebraic sum of the EMF in the circuit is equal to the algebraic sum of the potential drop across the components resistances in the circuit. So that is the statement of Kishkov's voltage law, and while applying this law, we'll have to use a rule which is known as a loop rule. And in this loop rule, the positive value of the current is taken when the loop is in the direction of the current, and the EMF is taken positive when the loop is from negative to positive terminal of the cell. So to understand this loop rule, we'll consider a closed circuit shown in the figure. And here we have two resistors of resistance R1 and R2, and we have two cells of EMF E1 and E2, and a current I is flowing in this closed circuit. And here we can choose a loop from A to B, B to C, C to D, and D to A, or another loop in the direction from A to D, D to C, C to B, and B to A. So let's first choose the loop from A to B, B to C, C to D, and D to A. And according to KVL, for this loop, since the direction of the loop for the EMF is from A to B, B to C, D to A. Okay, the direction is from D to A, so the EMF is taken positive because it is in the direction from negative to positive. So you can see here for E2, okay, since E2 is negative at D and positive towards A, hence E2 is positive, and E1 is also negative towards D and positive towards A. So E1 is also taken as positive. Then we come to the current. Now in the current we have A to B, B to C, D to A, and again here the loop is from B to C. So the current is flowing in the same direction as the loop. You can see here in the diagram the current flows from A to B, B to C, C to D, and D to A. And the loop is also in the same direction as that of the current. Hence the current is taken to be positive. So we have here IR1 plus IR2. So the algebraic sum of the EMF, E1 plus E2, the sign is taken care of, is equal to the algebraic sum of the potential drop across the resistance R1 and R2. And again here also the sign is taken care of by using the loop rule. Then we have another loop, A, D, C, B, A. So in this case, you can see that the loop is from A to D. That is for E1, it's from positive to negative. And then for E2 is also from positive to negative. The direction of the loop is from positive to negative. Since the direction is from positive to negative terminal of the cell, the EMF in both the case, in both of the cell, is taken to be negative. Hence we have here minus E1 minus E2. And the current, again the current is in the direction from B to C, but this loop which we have taken is from A, D, C, B, A, which means the loop is from C to B, which is in the opposite direction of the current. Hence the current is taken to be negative. Hence we have minus E1 minus E2 is equal to minus IR1 minus IR2. The negative sign is because of the loop rule. Hence again we have this one, the sum of the EMF E1 plus E2, the sign is being taken off by using the loop rule, is equal to the sum of the algebraic sum of the potential drop across R1 and R2. Again the sign is taken care of by using the loop rule. So you can see here that the negative sign can be taken common in both the sides, and we can cancel the negative sign to get E1 plus E2 to be equal to IR1 plus IR2, which is the same as that of the first case or the first loop. So here again you have to note, for this Kishkov's voltage law you have to apply the loop rule. In the loop rule, the positive value of the current is taken when the loop is in the direction of the current, and EMF is taken positive when the loop is from negative to positive. Otherwise, it will be negative. So this law is based on the principle of conservation of energy. Here, the energy, okay, from the EMF, the chemical energy from the cell of EMF E1 and E2, both these energy is being converted into electrical energy across the resistance R1 and R2. Hence we have the sum of the EMF in the left hand side and the sum of the potential drop in the right hand side, because there's a conservation of energy. All of the energy in the cells is being converted into another form of energy. For example, if R1 and R2 are bulbs, then that energy will be in the form of light. The electrical energy will be in the form of light or of heat. So that's why this Kishkov's voltage law is based on the principle of conservation of energy. Next is the Wheatstone Bridge. Now, a Wheatstone Bridge is one of the accurate arrangements for measuring an unknown resistance. And a meter bridge is one of the practical application of this Wheatstone Bridge. So this Wheatstone Bridge is actually consists of four resistors P, Q, R, and S connected to form a quadrilateral. Okay, as shown in the figure, and we have a battery of EMF E connected between the point A and C, and a galvanometer of resistance G is connected between B and D. So this is a Wheatstone bridge, and there is a principle in which this bridge is working, and that principle working of this Wheatstone bridge, okay, it is based on the fact that if the ratio of the resistance P to Q equals the ratio of the resistances R to S, that is P divided by Q is equal to R divided by S, then the bridge is said to be balanced. Now under this under this condition, the potential at B and the potential at D is actually equal. So we have VB to be equal to VD. And since the potential is equal, if we take the difference, the potential difference, VB minus VD, we will get it to be equal to 0 because they are equal. And since there is no potential difference, there will be no current flowing through the galvanometer. Hence, the current through the galvanometer, which is represented by IG, is equal to 0. Now again, this is by using Ohm's law. IG is equal to V divided by G. Hence, under the balance condition, that is when P by Q is equal to R by S, no current will flow through the galvanometer. So this is the principled working of the Wheatstone bridge. Now we can prove the Wheatstone bridge principle by using Kishkov's laws. So we consider the Wheatstone bridge, and in the Wheatstone bridge at junction A, the current entering is I, and the current leaving the junction is I1 and I2. So I here is equal to I1 plus I2. So here the current I is split into two parts. I1 flows through P, and I2 flows through R. Then again, you consider the junction B. At junction B, the current entering is I1, and the current leaving is Ig. One part is Ig, which flows through the galvanometer G of resistance G, and the remaining part is I1 minus Ig, which flows through the resistance Q. Then this Ig will meet at D with the current I2. As you can see here, I2, it flows through R and it meets at D with Ig. So here the current entering at junction D will be I2 and Ig. And according to Kishkov's current law, the current leaving, that is the current flowing through S, should be equal to the sum of the current entering, that is I2 plus Ig. So the current flowing through the resistance S is equal to I2 plus Ig. And these current I1 minus Ig and I2 plus Ig will meet at point C, and the current flowing away from the point C is equal to I. Then we can use Kishkov's voltage law also. Here we'll have to use Kishkov's voltage law and again apply the loop rule. So here, on applying Kishkov's voltage law, we select a loop which is ABDA. And in the loop ABDA, okay, we do not see any battery, hence the EMF is 0. But as the current flows through P, current I1 flows through P, there's a potential drop across P. Ig flows through G, there's a potential drop across the resistance of the galvanometer of resistance G. and since I2 flows through R, there is a potential drop across R. And using the loop rule, we have selected ABDA to be the loop. Since I1 is in the direction of AB, it is positive. And since IG is in the direction of BD, it is positive. But I2 is in the opposite direction of DA. Hence, this is taken to be negative. So the algebraic sum will be I1P plus IgG minus I2R is equal to 0 since we have no battery, since the EMF is 0. Then again we choose another loop, which is BCDB. Again here also I1 minus IG is in the direction of the loop, so it's taken to be positive. And IG is in the opposite direction of the loop. The loop is from D to B, so IG is from B to D. Hence IG is negative. Similarly, I2 plus IG also, since the loop is from C to D, which is in the opposite direction of I2 plus IG, hence this I2 plus IG is also taken negative. Hence we have I1 minus IG into Q minus I2 plus IG into S minus IgG is equal to 0. Again here also, since there is no battery, the EMF is 0. Now under balance condition, okay, the current Ig is equal to 0. So under this condition, your Ig is equal to 0, and putting Ig in the above equations, two equations, we have in the first equation we have I1P minus I2R is equal to 0. Since Ig is equal to 0, we have this equation. Or here we can take this minus I2R in the right hand side. You will get I1P to be equal to I2R. Then again in the above equation, putting Ig to be equal to 0, we'll get I1Q minus I2S to be equal to 0. Again, putting this minus I2S to the right hand side, we'll get I1Q is equal to I2S. So we have two equations, 1 and 2, under the balance condition. Now dividing equation 1 by 2, we'll get I1P divided by I1Q is equal to I2R divided by I2S, and I1 cancel, I2 cancel. So we have P by Q is equal to R by S, which is the required condition for the bridge to be balanced. So this is the proof of the Wheatstone Bridge principle. Here we are making use of Kishkov's voltage law and current law. Now we come to the practical application of the Wheatstone Bridge, that is the meter bridge. Now a meter bridge is constructed on the principle of a balanced Wheatstone bridge. It consists of a Constantan wire AC of 1 meter length stretched between two copper strips. A meter scale is fitted parallel to the length of the wire. Now a central copper strip is fitted to provide two gaps across which a resistance box R and an unknown resistance X is fitted. Now one end of the galvanometer G is connected to the junction D, and another end is connected to a jockey, which can be slided over the wire to balance the bridge. And if B be the point on the wire when the bridge is balanced, that is the current through G is 0, then the B is called the null point. And if P and Q be the resistances of the wire of length AB, which is equal to L, and BC, which is equal to 100 minus L respectively, then the P by Q is equal to R by X, which is the Wheatstone Bridge principle. So here, this is the practical application of the Wheatstone Bridge. And here we have again 4 resistance, P, Q, R, and X. And X is the unknown resistance. So we can use the meter bridge to find the unknown resistance. And here the important point is to remember this null point. Now, a null point is a point in the wire when the galvanometer shows a zero deflection, which means that the current through the galvanometer is equal to zero. So here, after connecting all the instrument or the all the devices, what we'll have to do is we'll have to slide the jockey on the wire, and we'll have to find a point on the wire which shows a zero deflection on the galvanometer, and that point is known as the null point. And we have to measure the length L, which will give us the resistance P, and the length 100 minus L, which will give us the resistance Q. Now the resistance of a wire of length L and area of cross section A is given by rho L by A. Hence the resistance P is equal to rho L by A. And the resistance of the wire of length 100 minus L, which is Q, is equal to rho 100 minus L divided by A. This formula we have done while studying resistances and the factors in which the resistance depends upon. So here we have P to be equal to rho L by A, Q is equal to rho 100 minus L by A. Now we divide P by Q, we'll get L divided by 100 minus L. Under the balance condition, we know that P by Q is equal to R by X. Therefore, putting the value of P by Q, we'll get L by 100 minus L is equal to R by X. Hence, the unknown resistance is equal to R 100 minus L divided by L. So as you can see here, that X is equal to R, which is known to you, and this has to be taken out from the resistance box, and 100 minus L. Now this L has to be found out. If you know the null point, then we'll know this distance L. So here in this experiment, okay, to find or to measure the unknown resistance X, we'll have to find the null point and measure the length L. Once we know the length L, we can find out the unknown resistance X using this formula. Now next is the potentiometer. This is another electrical device, and this is used to compare EMFs of two cells or to measure the internal resistance of a cell. Now the principal working of this potentiometer states that when a constant current pass through a wire of uniform area of cross section, the potential drop across any portion of the wire is directly proportional to the length of that portion. So that is the principle of the potentiometer. So basically here we are making a constant current pass through a wire of uniform area cross section, and on doing so, the potential drop across any portion of the wire will be directly proportional to the length of that portion. And the potentiometer here consists of a segment of wires of uniform area cross section stretched between two copper strips. Now each segment of wire is 100 centimeter long. Meter scale is usually fixed parallel to its length. A battery is connected across the two end terminals, sending current through the wire, which is kept constant using a rheostat. So this is the circuit diagram of this potentiometer, and here in this diagram we can see that the potentiometer, the wire has 4 sections. So each section is of length 100 centimeter. So it starts from A, then it goes 100 to the next wire, 200 to the next wire, 300 to the next wire, 400, ends at B, and then it's connected to the rheostat, and then to the battery, and then to the ammeter. Now in the diagram, I is the current flowing in the wire. Now this V is a voltmeter. It is used to measure the potential drop across any portion of the wire. So here, if AC is the portion of length L, Then the potential drop across this portion AC of length L is given by Ohm's law, that is V is equal to IR. R is the resistance of the portion of the wire of length L, that is from A to C. So now R, we know that R is equal to rho L by A, hence V is equal to I rho L by A. Now the principle of the potentiometer, it is based on the fact that I is to be kept constant, and the area of cross section is also uniform. So here I, in this formula, I is constant, and the area cross section is also constant. And if we choose the same material of wire, then the rho is also constant. So here I, rho and A, they are constant, hence your V is directly proportional to L. And this constant is denoted by K, and this K is actually equal to I into X. And this X, if you, from the formula itself, you will get X to be equal to rho by A, and from the definition of resistance and resistivity, rho by A is equal to R by L, which is the resistance per unit length. So K is equal to Ix, and X is the resistance per unit length. So here also from the equation to V K is equal to KL, we have K to be equal to V by L. Now this V by L, potential difference divided by the distance L, this is known as the potential gradient, which we have done in chapter 2. So here you need to remember this principle of the potentiometer, that the current has to be kept constant, and the area of cross section of the wire has to be uniform throughout. Then only the potential drop across the portion of the wire is proportional to that length of the portion. Now, one of the application of this potentiometer is to compare the EMF of two cells. So here we have two cells of EMF E1 and E2, and to compare these two cells, the EMF of the two cells, we have to make the circuit as shown in figure. After making the circuit, what we'll have to do first is that we'll have to connect the plug between the terminals 1 and 3 of the two-way key. Then we slide the jockey over the wire to obtain a null point C. A null point again is a point when the galvanometer shows a zero deflection. Now under this condition, the potential drop across the portion AC will be equal to the EMF of the cell E1. Hence this E1 will be directly proportional to L1, which implies that E1 is equal to KL1, and K is a constant. And after we have found out this L1, what we do next is we unplug the plug from the key, the two-way key 1 3. Then we connect the plug between 2 and 3, and what we do is again we obtain a null point on the wire, and if L2 be the length between A and the null point of the wire, then in this case the EMF E2 will be directly proportional to this null point, will be directly proportional to the length of the wire. Hence your E2 will be equal to KL2. So we have two equation, 1 and 2, and we divide the two equation. What we'll get is E1 by E2 is equal to L1 by L2. And then this is how we can compare the EMF of two cells. So by taking the ratio, we'll get the EMF of the two cells. So here remember, you'll have to find the null point in each case for E1 and for E2. The second application of a potentiometer is to measure the internal resistance of a cell. Now to measure this internal resistance of a cell, what we do is we set up the circuit as shown in the figure in order to find the internal resistance R of a cell of EMF E. What we do is we first open the key K. Then we obtain a null point on the wire. Say C is the null point when the key K is open, and say L1 is the length of the portion from A to C when the key K is open. Then again here the EMF E of the cell will be directly proportional to the length L1, and then which implies that E is equal to KL1. Then what we do is next step after we've got this L1, we close the key. Now with the help of the resistant box, we introduce this resistance S. Again here also after closing the key, what we do is we obtain a null point, and if L2 be the length from A to the null point on the wire, then the terminal potential difference V of the cell will be directly proportional to this length L2. Hence we have V to be equal to KL2. Then we divide E by V. We get E by V is equal to L1 by L2. Now the internal resistance R is actually given as R equal to E by V minus 1 into S. This is the expression for internal resistance of a cell, which we have obtained in the last lecture. Then here E by V is equal to L1 by L2. Therefore R is equal to L1 by L2 minus 1 into S. Then the R here will be equal to L1 minus L2 divided by L2 into S. So here, knowing the values of this L1 and L2, we can find out the internal resistance of the cell.